Hello, let's get back to discrete random variables and talk a little bit about calculating mean, variance, and standard deviation. Just like back in Module 3, where we had a quantitative variable and you learned how to calculate the mean, variance, and standard deviation, we can also calculate the mean, variance, and standard deviation of a discrete random variable. The formulas may look a little different to you, but I will explain why as we go along. Let's start with the mean. The mean actually gets a new name. It's called the expected value of the variable. And here's our formula for the mean or expected value. First, we're going to give it a new notation. E of x stands for the expected value of x. But it's exactly the same as a population mean. The reason we say a population mean, by the way, is we usually think of a discrete random variable as a depiction of the way a population should look. For example, if x is the roll of a die, and x therefore can take on the numbers 1, 2, 3, 4, 5, 6 with probabilities of 6, the 6th, etc. That's theoretically what we would expect the distribution to look like if you rolled the die long enough. That is, if you had the entire population of rolls. So we'll call it the population mean. Now again, the formula over here may look a little different. We're going to take each value of x, multiply it by its f of x, its probabilities, and sum them. Basically, this is actually a version of the weighted mean formula. We're taking the values of x and weighting them by their probabilities of occurrence, and then summing the result for all values of x. Sometimes students get confused here. They think, oh, I have to add up the numbers and divide by n again, like the way we did back in Module 3. Now, you're not going to have a division by n because it's basically taken care of when you weight the values of x by their probabilities. Let's get to the formulas for variance and standard deviation, and then we'll do some practice calculations. The variance, again, we're going to give it some new notation. We'll often call it v of x, but we could again call it sigma squared, the population variance. If you look at the formula here, summation x minus mu squared f of x. Again, you would have to calculate the mean first, and remember the mean is just the expected value. You'll have to take the deviations around the mean, x minus mu, square those deviations, multiply them by their f of x's, in other words, you're weighting them by the f of x's, and then sum them for all values. I like to give an alternative formula that I think is, in some cases, a little bit easier. The variance of x is equal to e of x squared, that is the expected value of x squared, minus the mean squared. One of the reasons I like this alternative formula is, remember, the mean is just the expected value. So if you calculate the expected value of x first, you can just square it to get this second part. Then the only thing we have to calculate is this term, the expected value of x squared. To do that, you square the x's, multiply them by the f of x's, and add it up. Let's take a look at a sample problem, and we'll use both formulas at first and show you that they are equivalent. As long as you haven't rounded the mean, you will get the same answer. Oh, one last thing before we go to that sample, or to the example we're going to look at. As always, remember that the standard deviation is the square root of the variance. Sigma is the positive square root of sigma squared. Okay, let's go back to our TV sales. X could be 0, 1, 2, and 3 with f of x's probabilities 0.1, 0.3, 0.4, 0.2. If you want to calculate the expected value, you have to multiply across. Let's set up a column for x f of x. 0 times anything is 0, 1 times 0.3 is 0.3, and so forth. And then we simply sum those quantities. Turns out here you will get a sum of 1.7 as your expected value. And again, we can call that mu, the mean. Now, if you want to calculate the variance using the first formula that we had a minute ago. Again, we already know the mean mu is the expected value, 1.7. We're going to have to do all the deviations around the mean, square them, multiply by the f of x's. So I have a column here for x minus mu. It's just taking these numbers 0, 1, 2, 3 and subtracting 1.7 from each of them, and you will get the numbers in this column. Square those numbers, then multiply those numbers by the f of x, corresponding f of x's. So 0.1 times 2.89 is 0.289, and so forth. Finally, we add those up in this column. We add up the squared deviations around the mean times the probabilities, and we will get a variance of 0.810. If the variance is 0.810, the standard deviation is the square root of that, or 0.9. If you want to use the second formula, again, we already know the mean mu is 1.7, and we need to square that. The only other thing we need here is to square the x's and add and multiply them by the f of x's and add up the result, and then plug that into the formula. So that's why I have two other columns here at the end. X squared, just taking the values of x and squaring them, and then taking those squares and multiply them by their corresponding f of x's, their corresponding probabilities. 0.1 times 0 is 0, 0.3 times 0.1 is 0.3, and so forth. Those add up to 3.7. Then we plug everything in our second formula. The variance is 3.7 minus 1.7 squared, and again turns out to be the same as we had before, 0.810. Both formulas will give you the same result unless you've rounded the mean in some way. You don't need to use both formulas, whichever way you feel most comfortable with. And again, a little bit later, I'll be showing you how to do this on your calculator. Let's do a second example. A firm has estimated 4 possible profit levels for next quarter, which we will call our variable x in thousands. Find the expected value, variance, and standard deviation of this random variable. So notice we have 4 possible profit levels, minus 50 or a loss, 25, 50, and 100, with the following probabilities, 0.2, 0.4, 0.3, 0.1. Multiply across, again, calculate x times f of x to get you this column right here. Add those up, that adds up to the expected value, or the mean, which turns out to be 25,000. Now I'm just going to use the second formula for the variance this time, rather than doing it both ways. We'll have to square the x's, which gives you this column of numbers. Minus 50 squared is 2,500, 25 squared is 625, and so forth. And then multiply those by the f of x's to get this last column. Add those up, you get 2,500. Put it in our formula. You take 2,500 minus the expected value of x squared, or the mean squared. Gives you a variance of 1875. Take the square root of the variance, and you will get a standard deviation of 43.3. Remember again, this was in thousands, so we had an expected or mean value of 25,000 and a standard deviation of 43,300. On your calculator, if you have a TI 83 or 84, the method of doing discrete random variable mean and variance is very similar to one variable statistics that you learned in an earlier module. Put the values of your x variable in a list, let's say L1, and then put the associated probabilities, the f of x's, in another list, let's say L2. Press your Stat button, move over to Calc, choose number 1 variable stats, and press Enter. Now the calculator wants to know where your variable is. You're going to enter L1, comma, L2, and press Enter. The calculator realizes since you pressed 1 variable stats that you really only have one variable, so it will assume that what's in L1 is your variable, and when it sees that you put L2 in there, it knows that those become the weights for the calculation. And this will give you the mean and variance, and I believe the mean and standard deviation actually. A few little notes about expected value and variance, and you don't get worried about these. There's very few places that we're going to use these, but they can be useful in some cases. Some of these are obvious. They're similar to things that we had earlier. The formulas we've given you here deal with the expected value and variance of a discrete random variable. Let's start out with what if you had a constant? Let's C be a constant. Well, first, and this one should be fairly obvious, the expected value of a constant is just the constant itself. That's equivalent to saying the average of a constant is the constant. Just like back in Module 3, if you had the numbers 5, 5, 5, 5, 5, and they're all the same, well, the average is going to be 5. The same is true with a discrete random variable. Supposing I had a 6-sided die, but all 6 sides had the number 3 on them. Well, every roll is going to be a 3, and the average roll is going to be 3. So the expected value of that constant is just the constant. The next rule, the variance of a constant is, of course, 0. By definition, a constant doesn't vary, so its variance is 0. The next rule, the expected value of a constant times a variable. The basic idea here is you can pull the constant out in front of the expectation sign. This is equal to the constant times the expected value of the variable. In other words, for example, on one of my earlier examples, had I taken my random variable x and multiplied every value by a constant, say 10, I've basically just multiplied the expected value of that variable x by 10. The variance of a constant times a variable, you can pull the constant out in front, but you have to square it now. It's equal to c squared times the variance of x. That might not be that surprising if you remember that a variance, in a sense, squares all the units of measurement in a problem. And finally, one last rule of expectations and variances. The expected value of a sum of two variables is basically the sum of the variables themselves, the expected value of the variables themselves. So if I define a new variable x plus y, the mean or expected value of that new variable x plus y is equal to e of x plus e of y. Okay, let's do a couple little applications of expected value and variance. There's lots of places that apply probabilities and expected values. One place is the insurance industry. Throughout your life, you're going to be paying car insurance, life insurance, house insurance, all sorts of insurance. And insurance rates, or so-called premiums, have a lot of probability analysis behind them. Let's take a very simplified example. Consider house insurance against, say, fire. Let's say we've got a house that's worth $300,000. And in any year, we're just going to consider two alternatives, and only two. Either the house burns down, and it's a total loss, or it does not. Now, in reality, to make this more realistic, we could have added in partial losses. Maybe 10% of the house burns down, or 20% of the house burns down. But here we're just going to make it simple for illustrative purposes and just consider two possibilities. Let's define a random variable x to be the loss to the insurance company. So we have two possibilities here. If the house burns down, we'll assume the insurance company is out $300,000. We'll assume it's a complete loss. If the house doesn't burn down, then the insurance company is out nothing. Their loss is 0. Insurance companies hire people known as insurance actuaries who do a lot of the work estimating probabilities on such things. Let's take a look at our variable X so far. Our variable X has two possibilities. The insurance company either loses 300,000 or loses zero, depending on whether there's a fire or no fire. Let's make up some probabilities. Let's assume that in any time period, say like a year, the probability of no fire, let's say, is 0.999. And the probability of a fire is 0.001. It's probably even smaller than that, but I just used these for, again, illustrative purposes. The first thing we can do here is calculate the expected loss to the insurance company. 300,000 times 0.001 is 300. 0 times anything is 0. Add those up and you get the expected loss to be $300. Now that could be useful information to the insurance company in helping them set their premium rates. Just the cost of this insurance on average is going to cost them $300 a year. And of course the insurance company likely has other costs like employees' costs, wages and salaries, and so forth. But this could be a first step in just estimating the insurance cost of offering such a policy. Another place that uses expected value and variance type concepts is in a whole area known as risk aversion. There's been a lot of research and work done in the area of risk aversion. Let's kind of play a little game here. Let's consider two alternatives. Let's say you've got $1,000 to invest, and we're going to give you two choices. You can either have, number one, a sure gain of $500 with absolute certainty, or a 50% chance of a gain of 1,000 and a 50% chance of a gain of 0. The second option there is what I call the coin flipping option. It's like flipping a coin. Heads, you get 1,000. Tails, you get 0. First, I ask you, what is the expected gain with each strategy? If you think about it for a moment, we can figure these out pretty easily. The first one, just like going back to one of our rules a minute ago, remember the expected value of a constant is the constant itself. So the expected value of a sure gain of $500 is $500. The second one also has an expected value of $500. If you flip a coin in a sense, 1/2 probability times getting 1,000 or gaining 1,000, 1/2 probability of getting 0, you average those out, the average gain will again be $500. So both 1 and 2 here have the same expectation. They have the same expected value of $500. Which do you prefer? There's no right or wrong answer to this, but think about it for a moment. If you were offered a choice between a sure gain of 500 or you could take a risk, you could flip a coin, 50% chance of you getting 1,000, 50% chance of getting nothing. What would you prefer? Now let's change the game slightly. Let's go to option B, we'll call it. This time we're going to give you $2,000 to invest, and you have to choose between a sure loss of $500 or the coin flipping option again, a 50% chance of losing 1,000 and a 50% chance of losing nothing. Again, a little bit of mathematics, and you should be able to figure out that the expected loss with each of those two strategies is exactly the same. Again, option 1 is a constant. You're definitely going to lose $500, so that average loss is 500. Option 2, which is like the coin flipping option, 50% chance of losing 1,000, 50% chance of losing nothing, averages out to a loss of 500. Again, we ask the question, which do you prefer? Would you rather have the sure loss of 500 or take the risk? Now, one of the reasons this is interesting is if we think the world is kind of composed of people who like to take risks, risk takers, and people who don't like to take risks, risk avoiders. Well, let's start with the risk avoiders. Whether it was game A or game B here, if you don't like to take risks, well, then you could have taken the sure gain or the sure loss and avoided the coin flip option. If you're a risk taker, you'd probably flip the coin in either case. Flip the coin in the case of the gain, flip the coin in the case of the loss. Yet interestingly, research has been done and found that that's not generally what people will do. Most people are risk averse in situation A. In other words, they'd rather take the sure gain, they'd rather not flip the coin. And an overwhelming majority of people do take the risk in situation B. They'd rather flip the coin to avoid a sure loss. This has led to a whole branch of economics, actually. It's something referred to as prospect theory. Here I've given you a link you can go to in Wikipedia. A gentleman by the name of Daniel Kahneman won a Nobel Prize in economics for his work in prospect theory. And you can read about that if you happen to be interested in it. That is the end of part 2, and we'll be back in the next section to talk about a particular discrete random variable called the binomial distribution.